Next speaker is Alex Gamerick. Is that close?
Perfect.
Alex Gamerick, currently a Master of Applied Science student at Carlton University down the road in Ottawa. His research focuses on the development of new and useful scientific instruments and their use techniques. He's working on developing a tunable diode laser absorption spectrometer, TLAS, I don't know how to pronounce that acronym, for gas identification and characterization for use in planetary and satellite penetrators. Alex is going to talk to us about searching for extrasolar life. So, over to you. I will hover at about the 10-minute point.
Sounds good. Hello, everyone. It's an honor to be here. This is my first conference presentation, so treat me well. I hope I'll give you guys some good information and show you some of the research that I've done to date. So my name's Alex. I'm here representing Carleton University and the University of Winnipeg. My co-authors are Dr. Alex Ellery and Ed Cloitis from Winnipeg. And I'm here to talk to you what we propose as a minimalistic multi-instrument payload for astrobiology for an interstellar mission. I'll offer our views on what consists of the definition of life that we use to select all the instruments that we have, and some biomarkers that we would potentially target. And then I'll go into the actual instrumentations as well. So, getting into it. Just for the sake of argument, we're not really concerned about what interstellar or celestial body we're at or how we got there, just the instruments that we'll be talking about. The idea is that we're developing a payload that could be readily adapted for a penetrator or a lander. So the instrument suite, as we've identified, follows a drill-down hierarchy, common to most planetary rover missions. So target site and sample selection would be accomplished with a macroscopic and then a close-up imager as well. So the macroscopic imager would be a UV, vis, or IR panoramic camera for large-scale geological feature identification, and we would use that to identify areas of interest for actually going to and detecting targets and samples. The close-up imager would be used for actual sample identification. This is a pretty common planetary science approach, and there are actual instruments already with flight history, like the microimager on Spirit and Opportunity and Mastcam-Z on Perseverance, that accomplish this same task. So it's nothing innovative here. Specifically, that's just for like target site identification and sample identification. The actual information that we're looking for that constitutes the biological payload identification comes from contextual information like general mineralogy and supplemental biomarker identification, that we would use an integrated sensor consisting of a combined infrared Raman spectrometer, a laser-induced breakdown spectrometer, a tunable diode laser absorption spectrometer, and a confocal microscope. So that's quite the integration task, but we believe that it's doable. And the final part of our payload would consist of the direct astrobiological measurements. Those would be made with a protein chip could be made with a protein chip employing molecular imprint technology, and specifically Oxford Nanopore's MinION DNA sequencer. So the goal of this payload is to integrate as many instruments capable of providing complementary contextual information and supplemental biological information into a single instrument to reduce payload size, power requirements, and computational requirements as well. So initial deployment, if this was actually to be developed, could be to Mars, Europa, or Enceladus as a proof of concept flight. So to specifically further discuss the integrated instrumentation suite, as that is quite the ambitious goal, of the 4 instruments. Raman spectrometers, laser-induced breakdown spectrometers, the TLAS, and confocal microscopes have all been well studied individually. There are numerous papers out there that you can read to learn about how to design or use these. Their use cases are quite well researched as well. These serve as contextual instruments. They can define and identify a whole bunch of mineralogical and biological or biomolecules. Sorry. I lost where I was. So it's interesting to note that in some way, shape, or form, significant development has been made on the different combinations of this instrument. So Raman has been proven to be integrable with a confocal microscope and with a Libs spectrometer separately. And recently, the TLAS has been proven to be integral with a Libs as well. So it's not far-fetched to assume that all of these separate instruments can be combined and integrated into one, especially because they all have essentially the same components. They all have a laser, a detector, and just various different optics as well, but they all employ relatively the same principle. So going on to the biomarker identification, we are looking at the Joycean definition of life as described by Hillary. So we define life as something that must store genetic information and it must be capable of self-replication. So for us, we take this as DNA and RNA as direct biomarkers for that. It also must have a self-sustained metabolism, meaning that it can acquire and use excess energy. And for us, this means that we're looking for enzymes, proteins, and amino acids that are common in life as we know it. Additionally, it must be self-encapsulated. This allows us to target specific enzymes and compounds that make clear delineations between like bacteria as we know it and the surrounding environment. We assume that these are direct biomarkers and evidence of life. So to just split that up, what we believe it is. So we identify biomarkers to be either ambiguous or non-ambiguous. An ambiguous biomarker is something that is or can be commonly produced abiotically. So it has a physical phenomena that is not required. Life isn't required to develop it. And what we identify as a non-ambiguous biomarker is something that, so far as I know, and recent literature shows, is developed only by biotic processes. The list that I show there was identified in 2014 by Edwards, and it's a non-exhaustive, but we take it as truth for what a non-ambiguous biomarker is. So to discuss what an ambiguous biomarker are, those include like atmospheric compounds that are indicative of life, such as methane, oxygen, carbon dioxide, and the sorts, indicative isotopic ratios of specific chemicals, because it's been shown that metabolism in certain bacteria and ourselves as well prefer certain isotopic ratios over others of specific chemicals and elements. So if there is a ratio imbalance between what would occur naturally, that could be a non-ambiguous or an ambiguous indication that there could be life. The general idea that we're trying to employ is that it's common in the astrobiology community is that we're merging astrobiological instrumentation, specifically with geological and geochemical instrumentation. And the mission payload that we have is very well suited to that. So you start off with a overall global contextual realization with the macroscopic imager and then the close-up imager. You acquire what the global and local atmosphere and surrounding environment looks like, and then you can do drill down from there, analyze specific samples for organic and biomolecules or direct evidence of life. just to move on to the specific instruments that I mentioned and why we chose them, I'll first talk about the Raman spectrometer. It forms the basis of all in the entire integration of our proposed integrated instrument, because it has been more commonly combined with the other instruments so far. Like, it has been combined with laser-induced breakdown spectrometers and confocal microscopy. There's an entire field of petrology where it's commonly implemented as an integrated instrument. So just adding extra, this kind of forms the backbone of our instrument. It's a non-destructive instrument. It requires no sample preparation, although some sample preparation is good. It measures altered scattered radiation off a sample from a known excitation source, and can be employed in a standoff or contact-based method. So it has been proven to work up to kilometers away from a sample, Raman spectroscopy specifically. Commonly, though, if it's used in standoff, it only works up to a couple meters in the space environment. It has extensive libraries on general mineralogical spectral response and some biological molecules as well, but there requires significant expansion on the specifics for that. We specifically proposed that this instrument would use an infrared laser because that is the strongest and most well-suited laser excitation source for biomolecules. Like, for example, Perseverance uses a green laser, so in the visible spectra. That is because it's also being highly focused on mineralogy. Now, a Raman spectrometer in the visible wavelength is more suited for mineralogy, but for biological identification, the IR spectra is best. The two figures here just show specific instruments that I myself have taken a part on. On the left is a standoff instrument, and on the right is a contact-based instrument. The Libs spectrometer is a slightly destructive instrument. It measures the elemental and chemical compositions of a sample. I say slightly destructive. It operates by focusing highly intense beams of light and ablating the surface of a sample. It ends up ablating nanograms, so not really ruining your sample there. It, similar to the Raman spectrometer, doesn't require any sample preparation as well, and can also be used in contact or standoff setups. There's extensive flight history for the Raman and the Libs spectrometers as well. The TLAS is my bread and butter, as it's the instrument that I've been working on for my master's. The image shown here is a proof of concept instrument developed at Carlton for use in a lunar penetrator, which was being built by Magellan Aerospace. So work is already being done on some of these instruments to miniaturize and ruggedize them for penetrators or rovers as well. So that serves to help promote our point. It is a non-destructive and non-evasive gas analysis instrument capable of detecting the presence, concentration, flow rate, temperature, and isotopic ratios, and molecular isotopologs with high precision and very quickly. So that suits our purpose as well. It would be a contextual instrument for our payload for atmospheric analysis and potential sample off-gassing detection. It has no flight history as of yet, but it was developed for the Russian Kazachok, I believe I'm saying that right, to be launched with ExoMars, but that was canceled due to the conflict. So it still remains to have no flight history, but I think it's an important indicator on the instrument itself's capabilities since it was completely integrated into a rover. Now, confocal microscopy, it's a microscope capable of very high resolutions at very low scales. micro to nano. It produces high-resolution, spatially resolved 3D images of samples. So that provides a wealth of information visually. It's used often in petrological analysis, so to determine rock grain structure. And that's important because based on rock grain structure, you can directly tell if water once flowed over whatever sample you're looking at, which is also a contextual measurement of if life could have been there. It's also, you could use it for sample identification, and it's quite easy to differentiate directly between organic and inorganic matter. So it would serve our purpose as well. And no, it doesn't have any flight history, but it has been integrated directly already with the Raman spectrometer and is used extensively in the biological field. Getting to the non-ambiguous biomarker instruments, the first we propose to employ is a protein chip, and we specifically want it to employ molecular imprinting technology. A protein chip is a high-throughput instrument capable of analyzing a cell's entire proteome, so all of the proteins, enzymes, and acetic acids inside it. It does require some sample preparation, so care would be taken on how that works. Molecular imprint technology involves the development of artificial compounds that directly bind to specific enzymes, proteins, and amino acids. So with this, you could target, say, rubisco, which is a compound in photosynthesis. That's what we would use it for. The second non-ambiguous biomarker instrument we propose to employ, it's a commercial off-the-shelf sensor, Oxford Nanopore Technologies MinION Nanopore instrument, and this has garnered significant interest in the astrobiology community, as far as I can tell, because it's capable of directly sequencing nucleic acids like RNA and DNA, which we consider to be a non-ambiguous biomarker, so that would be a direct detection of life. Work has been done since it was first released to prove that it is capable of working in the space environment, which is because it has no flight history as of yet. So Tyler and Agiori have shown that it's directly able to detect and quantify microbial life with unknown samples that they were using. And it has also been shown to work in the space environment. So specifically, I believe it was Sutton. Yeah, Sutton proved that the MinION instrument is capable of detecting microbial life with very little detection degradation in the harsh radiation environment of Mars. But in harsher environments, such as Enceladus, there was significant detection degradation. So work needs to be done on this instrument to space harden it and enable it. But that is the overall theme of what we are trying to work on. So just to say some work that we've done at Carlton, specifically, we are currently developing a TLAS for use in a penetrator. We have a proof of concept up and running, and we're working on miniaturizing that and making it a bit better. We've worked on Raman spectrometers, contact and standoff based. And additionally, we've worked on some delivery mechanisms. So if this was a rover, we've worked on developing drills that could potentially be used for the identification, i.e. you would have all of these integrated sensors in the drill head. So as you drill down, you could be directly scanning different depths, because it has been shown that biological material has better odds of surviving if buried under regolith. So that would be one possibility for this integrated system. The end goal with all what we've done here at Carlton so far with the TLAS and Raman spectrometers and the drill is to show that have the capabilities and are working on developing the capabilities of developing a full instrument suite and payload package ourselves in-house. That concludes my presentation. Thank you for listening. Okay.
Thank you. In TLAS, what is the tunability of the diode referring to, and what is the source and detector orientation with respect to one another?
So the tunability refers to wavelength tunability, because the tunable diode laser absorption spectrometer works on a gaseous species absorption spectrum. So as you scan through a set range of wavelengths with the laser, the gas that you're looking at, or if it's there or not, will absorb very specific wavelengths. And based on that, you can identify and quantify the gas that's there. The TLAS works based on light's interaction through the gaseous sample. So ideally, you want to, based on the physics of it, you want to have as much exposure of the radiation through the gas. So what we are using is a Harriet cell to bounce the radiation back and forth to effectively increase the path length. And depending on how good your optic systems are, you can go from a 5 centimeter actual distance between your laser and detector up to scales of like hundreds of meters. So it's well suited for miniaturization. Yeah. All right.
So a quick question on the RNA DNA detection on Mars in particular. We know that we have already contaminated Mars to some extent because our decontamination process is only good to a certain level. The other question related to that is that there's possibly rocks on Mars from the Earth, just like there are rocks from Earth on Mars, just like there are rocks from Mars on Earth. So question is, if you detect RNA or DNA on Mars, how do we know where it came from? And how long does it last by itself if it's not from a current or recently living organism on the Martian surface?
With regards to if we know it's from Earth or not, I don't have an answer for you yet. That would be something for me to further investigate because I'm not sure how that works. Ellery, my co-author, might have an answer to that, though.
Yeah, I'm an engineer, not a biologist. So my understanding is that you should be able to detect any common evolutionary heritage between Earth and, yeah.
Perfect.
Yes, the sensors that you're talking about seem to be very useful for in solar system investigation. My question is, has there been any thought given to materials in the sensors or chemicals necessary for investigation and the length of time they might be suitable? Interstellar missions are going to be multi-decade missions before you can actually get the sensors in place.
That's not something that I specifically have investigated yet, but from my current understanding of the material, oh, it looks like Ellery also has something to say. No worries.
If I only heard half the question, but if I interpret it correctly, you're worried about things like the survivability of the reagents over long periods of time. Yes. Okay. With the MinION, yeah, this is a problem. It's not a solved problem. With the protein chip, potentially by using molecular imprinting using polymers, that they could survive for however long they need to survive.
It's a good thing you answered because I misunderstood the question. Okay.
So, really interesting stuff. Have you considered adding in with all of your wonderful laser diagnostics, terahertz, time domain spectrometry as well? It looks like you might have the right lasers to make that happen, and that would give you direct chemical information on top of everything else you have, and with no reagents needed, thankfully.
Short answer, no, but that's a great suggestion. So I will take that and run with it and see if it would be a good addition.
Wonderful, thanks.
Sorry, can you just repeat what it was?
Terahertz time domain spectrometry. You can catch me later and talk about it. I do a little bit of that.
Perfect, thank you.
As one of the few biologists here, I'm a little concerned that some of your instrumentation is so focused on what we happen to have evolved on planet Earth, the MinION in particular, because there are a lot of other, possibilities besides the 4 canonical nucleotides that you have in DNA. And so you'd have to have that flexibility. So, and then I worry that the visual, you jump from a very large scale to, really nothing. And the confocal, you would only see something that was already autofluorescent. So I'm wondering about if you've considered something that's a little bit more agnostic, like a GCMS, going back to that sort of thing. And if you're going to go with the protein chips, there are an awful lot of molecules out there that the GCMS may be able to pick up for you. But I'm worried when you mention something like Rubisco, which what I happen to have worked on for my PhD thesis, there's an enormous variety of Rubiscos, and they're very large enzymes. So anyway, I'm a little worried that there are a lot of gaps that you could actually be finding life, and you would miss it.
That's very fair. I'm running for
I'm
help
sorry.
now.
I don't mean to sound as negative as I am, but I'd like to help you because I think there are some gaps here.
Sure. Yeah, I understand that completely. I mean, at the end of the day, we have to make decisions about what we search for. You find what you search for.
Right. But it would be tragic if you found it and you didn't know that you'd found it.
True. But then where do you draw the line? I mean, we could look at silicon-based life forms or something like that. We have to draw the line somewhere. We do understand, or at least you understand, biology on Earth pretty well. We have no examples of other biology. I mean, I believe something like PNA would be sequenceable by MinION. But yeah.
Well, for example, I would like any polymer that had some chirality to it. For example, that I think would be indicative. So you have
amino
a long
acids,
polymer that was all left-handed. That I think would be pretty good, evidence.
Yeah, and I think that's where the TLAS comes in, because with the TLAS that can detect things like, that's isotopic ratios. So you're looking at sort of like a chiral
the isotopic ratios.
We have. That's
no, I mean, you've got a huge amount there. I'm just trying to shadow box with it and make sure, let's make sure that you don't miss something, because that would be really tragic.
Yeah, I think if we're talking about an interstellar mission, we're kind of we're trading between having a huge instrument suite against the amount of payload capacity we have, and so we have to make decisions about that. We made a decision to actually start focus down and then expand that out. There are emissions of scale, to be sure.
Sure, maybe some more imaging.
I'm not interested in GCMS myself. We build instruments. I'm only interested in building interesting instruments. Sorry.
Thank you for your points, though.
Yeah, I had a similar question. How would your instrumentation package change if you were looking for life forms that evolved in a anaerobic environment that used high energy compounds, such as undersea vents that I believe they use high sulfur compounds for their source of energy?
Probably drastically.
Okay.
Sorry? Okay.
So if this idea of identifying a large preponderance of a certain chirality of a polymer is indicative of life, as you suggest, do we have an instrument that can measure chirality of polymers? That sounds like a hard thing to do. Is that something we can already package up and put on a spacecraft?
I'm assuming that GCMS that you referred to would be able to do that? Okay.
Polarizable lenses would be one way.
So yes.
The protein chip as well, because that's to be chirally sensitive. So that would detect left and right-handed
But since polymers are locked in place, you would need a way to identify it spectroscopically, since you are using light, and polarizable lenses are going to be really strong in that way.
Given this is Alex's first paper, I think good job. Good job, and I think you're learning that a lot of the interaction comes through the Q&A, and this will continue through the rest, because there's a lot of smart people in the audience with different backgrounds, so learn from them. So great. Thanks for this. Appreciate it. Take care. Thanks. All right.